Hello, everyone, and welcome to our today's Quanser YOUser webinar. We invited Dr. Jinjun Shan from York University's Lasson School of Engineering to talk about the work in his lab focused on multi-agent autonomous systems. My name is Zuzana Fabushewa, and together with my colleague Oliver Zhang, we will be your hosts and webinar moderators today.
Thank you, Sana. Hello, everyone. Thanks for joining us today. My name is Oliver, and I am the regional manager for Canada at Quanser. We have been working together with Lausanne School of Engineering at York University over the years, and especially with Dr. Shan. I just realized today that Quanser and Dr. Shan crossed paths back in 2003, which is almost 17 years ago. That's a long time ago. I had personally involved in quite a few teaching and research projects with Dr. Shan's team, and it has been our pleasure to have opportunity to support his work and to grow together. So for those who does not know him yet, here is Dr. Shan's official bio. Dr. Jinjun Shan joined the Department of Earth and Space Science and Engineering at York University as an assistant professor in July 2006. He was promoted to associate professor in July 2011 and full professor in July 2016, and serves as the chair of ESSE and undergraduate program director for the Space Engineering and Space Science program at York University. Prior to his appointment at York, he was a postdoc fellow at University of Toronto Institute of Aerospace Studies from November 2003 and a research assistant at Department of Manufacturing Engineering and Engineering Management at City University of Hong Kong from September 2002 to September 2003. He received his Bachelor of Engineering, Master, and PhD degrees, all from Harbin Institute of Technology, China, in 1997, 1999, and 2002, respectively. Dr. Shan was awarded the Alexander von Humboldt Research Fellowship for Experienced Researchers and JSPS Invitation Fellowship in 2012. He is an Associate Fellow of AIAA and a Senior Member of IEEE, and a professor and a professional engineer in Ontario since 2007. His current research interests are dynamics, control and navigation, smart materials and structures, multi-agent system, and orbit dynamics. He is the founding director of the Spacecraft Dynamics Control and Navigation Laboratory at York University. So now, without any further say, I will pass it to Dr. Shan to start the presentation, and I hope all of you enjoy it. Dr. Shan, the floor is yours now.
Okay, thank you, Oliver, for your introduction, and good morning, everyone. My name is Jinjun Shan, and today my presentation is on the multi-agent autonomous system, dynamics and control and navigation. However, I want to make a correction because during today's presentation, I'm not going to talk about the navigation, and I will focus on the dynamics control, although my group is working on the navigation for the multi-agent system. So, and first, Oliver already gave everyone the introduction of myself, and right now I'm a professor of space engineer at York University, and I joined York in 2006. Before that, I got my PhD from Harbin Institute of Technology in spacecraft design. And here is the research areas of my group, and we are mainly work on the dynamics control navigation for space and aerospace and the mechatronic system. And of course, the autonomous system and the multi-agent system are two research topics in my group. So this is also the topic of today's presentation. And this slide shows the my collaborators, and you can see Quanser is one very important collaborator in my career. And as Olive said, I have been working with Quanser since 2003 when I started my postdoc fellow at University of Toronto. Okay, so let's talk about the topic for today's presentation, multi-agent autonomous system. So actually on the slide, you can see multi-agent system. So you can see the first figure is a bird, and second one I believe is also bird. And we also have the fish and the buffaloes, and at the top and at the bottom. So you can see that is a spacecraft mission flight and also the drone swarm of the drones. So these are all the examples of a multi-agent system. So actually that brings to the topic of the today. And also I have to say my research on multi-agent autonomous systems started from the research on the spacecraft or aircraft for mission flight back to 2003 when I joined U of T. And during that period, I worked with my collaborator, Professor Hugh Liu, and we developed a method. We invented a method called the motion synchronization control for multiple dynamic systems. And we got two patents. One is US patent in 2010, and the other one is Canadian patent in 2016. So that is the motion synchronization. So basically, we want to synchronize the motion between multiple dynamic systems. So the system does not have to be a spacecraft or aircraft, and it could be any types of the dynamic system. And in terms of the multi-agent autonomous system, and this slide shows several research findings in my group recently. The first one is the new one under the NSERC Alliance. So basically the essential technology for autonomous system, theory, verification, and applications. And also I'm leading a D&D project on the effective human-machine cooperation with intelligent adaptive autonomous system. So basically, for that project, we are more we focus on the human-machine cooperation. And also in 2017, I got a certified grant to set up the York Research Facility for autonomous unmanned vehicles. Actually, we purchased Quanser's autonomous vehicle research studio. So actually, that is a picture shows you. This picture shows you our research facility at York University. And now you can see we got 6 Q drones and 4 Q boards, I believe. And also we also got some self-driving cars. So you can see actually the system is up and running since May 2019. We have been working on this. We have been using the facility to verify our controllers in the past year, or more than 1 year, since May 2019. And also, if you are interested in using this facility, and you can contact me, and we can see what we can do. And here I want to show you a video, and basically this video is just to show you the facility. I just show you this is a autonomous vehicle facility in our building, and now you can see the Q drone, and this is a very basic introduction to the Q drones. And we use the motion capture system to get the position and the orientation of the drone and actually any object. And that is a Q bot. And we also have the something we did several demonstrations to show you how can we play with the autonomous vehicles. And this is a multi-vehicle collaboration between the Q drone and the Q bot. And that is drone transportation. And please pay attention to the end of the mission, and you can see actually the vibration of the cable or payload is very small because we use a particular technology called the input shaping. And this is the drone delivery. Yeah, this is self-driving research currently under investigation in my group. pathway for my research in the multi-agent system. As I said before, we developed the method called motion synchronization control for multiple dynamic systems. And actually, since we had that technology, and we actually successfully applied that patent technology to instrument called the fiber pulse spectrometer. So that is the instrument led by myself and also supported by the Canadian Space Agency. So basically, the idea is to develop an imagery fiber pulse spectrometer for observation of the Earth's surface and aerosol. And the spectrometer has been validated through 2 successful high altitude balloon flight, which are 40 kilometer high. So one in Sweden and one in Australia in 2016 and 2017. And in May this year, I got another grant from the Canadian Space Agency, the same program FAST, to develop a miniature fiber pulse spectrometer for potential future satellite application. So you may ask why this is related to the multi-agent system. So the reason is, if you look at the fiber pulse spectrometer and pay it, so actually here we have the key component is the fiber pulse filter. So basically, this is the optical system which has 2 optical plates and separated by 3 piezo actuators. And the piezo actuators are used to adjust the gap spacing between the 2 optical plates. And keep in mind when we do, and actually that is called scan. So when we perform the observation, we need to change the gap spacing at a very high accuracy. Basically, it's a nanometer level. And also keep in mind when we change the gap spacing between the 2 plates, we also need to keep the 2 plates parallel. So that means we have 3 actuators, 3 piezo actuators, and we need to synchronize the motion between the 3 piezo actuators. So this is why we successfully applied the patent motion synchronization method to solve the gap spacing adjustment problem for this instrument. And actually, the instrument has been successfully developed in the past few years, and we had 2 successful balloon flights. So actually, if you look at here on the right, you can see the animation. Basically, this is the observation. This is the measurement we had for the instrument, and you can see the peak of the wavelength is moving. So that means actually the gap spacing is adjusted. So actually, we use the patent motion synchronization method to solve the problem, to get the synchronized motion between the 2 plates. Using the 3 piezo actuator. So actually, this is the one application of the motion synchronization method to the multi-agent system. And that is the fiber pulse spectrometer and the final design. I'm not going to the details. And actually, I just want to show you this very interesting flight in Kiruna, Sweden on September 3rd, 2016. And now this is a balloon, which is a helium, and it will go up, it went up to the 40 kilometer. And then now you can see we have our instrument on actually close to ground, and this is our gondola. And then we release the balloon and it will go up to the 40 kilometer altitude. And actually our instrument is looking down to measure the Earth's surface. And again, as I said, during each observation, and the gap spacing between the 2 plates are adjusted by the 3 piezos. So actually, this is multi-agent system. All right, so these are some pictures for our flights in Kiruna and Alice Springs in Australia, and yeah, so this is a very successful demonstration or mission, space mission. So actually, I want to show you here. Now you can see we have the actually the 2 figures shows the motion of the 3 piezos. Again, so as I said, the 3 piezos are used to change the gap spacing between the 2 plates. Now you can see actually the 3 piezos can be adjusted, can be controlled to follow the step input at a very fast response. And now you can see each step is something 19 nanometer, and the control can be done within half second. So that is a very good result we got. And actually, I have to say we did use the motion synchronization method to adjust or to control the 3 piezos. And now let's talk about the cooperative control of the multi-agent system. And in addition to the motion synchronization of the piezo actuator, and our group also did a lot of work on the cooperative control of multi-agent system. Here is the list of the controller or work we have done in the past few years. So we had done the distributed control, fixed time control, event trigger, and also we consider different communication topology. And we also developed controller fault tolerant control, and also we for space application, and we also have the rotation metric based attitude control, something like that. So next, I'm going to give you I'm going to mention several of our research in this area, the cooperative control of multi-agent system. And so the first one basically is the fixed time consensus under undirected graph. So now you can see this is undirected graph. So that means the communication between agent 1, agent 2 is it's a bidirectional, and same for agent 2 and agent 3. So that is the undirected graph, and the contribution or the novelty of this work, to be honest with you, and the fixed time consensus is not something new, and undirect or direct graph are not something new. And the novelty here is we successfully applied the input shaping to this multi-agent system. And if you know this input shaping, basically that is a technology applied to used for vibration control. Okay, so here shows the basic idea of input shaping, and the idea is to have the command shaped by impulse, and then the shaped command will be applied to the system. So this way, the vibration can be surprised. So actually, here you can see in our research the fixed time consensus under undirected graph, and we apply the input shaper under each. So actually, under each layer, so we can have a fixed time consensus controller only by adjusting the reference command of each agent. So actually, this work has been published in TIE, actually TIE in 2019. And here, we use the Quanser SRV02. Actually, we use the 4 of the system to verify to verify the controller we developed. And actually, let me play this again. So now you can see, actually, if you look at the 4 SRV, and actually the consensus has been achieved. And the next one is fixed time consensus under directed graphs, and the previous work is fixed time consensus under undirected graphs. Here is directed graphs, so that means now you can see the communication between the leader from the leader 1 to leader 6. So this is the one directional communication topology. And again, so in this case, we also applied the input shaper or input shaping technology to the communication edge. So that is, we can get the novel consensus controller. And also the conclusion is the settling time of this multi-agent system depends on the communication network structure only. So now you can see on this control, on this diagram, you can see we have input shaper under each communication edge. And also because the spatial structure, we were able to verify each link actually separately. So this why actually, let me see, yeah, should be here. So now you can see actually this is So that is experimental result, and you can see, I believe because we can verify each link separately. So this is why I only show you one SRV02 for this experiment study. And our next one basically is so this is the distributed adaptive control of under Quanser Euler language systems. And here we consider both the fixed and the switching graphs. Fixed, I mean, this is the simple. So fixed, that means the communication graph is fixed, is unchanged. However, we also consider switching graphs. That means during the mission and the communication graphs are switching. So that is more complicated. And here we use because this is the under-actuated Euler language system. So we still use the Quanser SRV02 with the flexible link for our test. I believe at that time we only have one such system, so that's why we only use one for agent 4, and for agent 1, 2, 3, they are all the simulation model in our work. And again, so this paper has been, I mean, this work has been published in Nonlinear Dynamics in 2019. Yeah, let me show you another time. Yeah, now you can see that is the distributed adaptive control of the under-actuated Euler language system. And keep in mind for this work, we let the spacecraft, sorry, not spacecraft, we let the flexible beam to track a set point. So that means if you stop at one location. So that is distributed adaptive control of under-actuated system. All right, so next one basically is the distributed fault-tolerant adaptive control. And because this is a fault-tolerant, and we consider from time to time, the system may have some uncertain parameters and some faults, actuated faults, and also external disturbance. So we designed the distributed fault-tolerant adaptive control to address this difficulties. And also in this research, and we developed the finite time observer to observe the leader's velocity. And here you can see we have 4 flexible links as a multi-agent system. And again, so we only use number 4. We only use hardware for number 4, and the number of agent 1, 2, 3 are all the numerical simulation. Numerical models. And here you can see, okay. Keep in mind in this case, the flex link is checking a sinusoidal function, I believe. It's not a set point. So you can see under this fault-tolerant adaptive controller, the flex link is able to track the design trajectory, considering the uncertain parameters, actuator fault, and also the external disturbances. All right, so that is the distributed fault-tolerant adaptive control. And next one basically is distributed iterative learning controller. The reason why we developed the iterative learning controller is because we consider the system has repeatable disturbance. So that is the reason why we apply, or why we use the iterative learning control. So if you look at the again, so this SRV02 from Quanser, now you can see, and this is a cable. I believe the cable is a cable to get the strain gauge measurement. So this is a flexible link, and it has the strain gauge at the root of the link to measure the deflection of the beam, and the signal will be passed through the cable and to the computer. And now you can see if you rotate the link, and basically the cable could be treated as a disturbance to the system. And also we consider that is a repeatable disturbance, because every time if you rotate the link follow let's say sinusoidal function, and then the cable can be treated as a repeated disturbance to the system. So that is the reason why we decided to apply the iterative learning controller for this multi-agent system, because we consider multiple of this dynamic system. And also, we also considered different other features of the system. For them, we also consider the uncertain parameters. So we applied adaptive control, and also the system has non-repeatable disturbance. So then we use the sliding mode controller for that. And for some data zones of the system and we also have the data zone composition. So basically, this is the distributed iterative learning control. Again, so our work has been published in Attribute TIE in this year. And here is basically this is the experimental result. You can see. Okay, and this is the iteration 1, and you can pay attention to the 2 agents on the left. Now you can see for the iteration 1, the motions are not synchronized. That is because the disturbance of the system and uncertainty of the system. And yeah, so this is the iteration 1. Let me put it in the 2 times speed. And as time goes, and you can see, for example, this is iteration 5. Now you can see actually the motion among the 4 agents have been synchronized. And that means actually our iterative learning controller works. I believe we also have, so actually I believe we have more than iteration 5. I think we do have, yeah, this is iteration 20. You can see actually all the motions of the multi-agent systems have been synchronized. And here we use, in this experimental verification, we use 4 SRV02 with the flexible link to complete the task. All right, so that is a distributed iterative learning control. And here is another research. Yeah, this is another research for the multi-agent system, and here we call this as a Kaufman operator-based attitude synchronization. So actually, the difficulty of the multi-agent system is if we have to consider the nonlinear system and the dynamics and the control system design are normally complicated. However, since the beginning of the multi-agent system, and there have been many very good results developed and proposed for the linear system. So I think one idea is if we can have a linear multi-agent system, and the many theories can be applied. So actually, Kaufman, I believe he proposed the idea of the Kaufman operator many years ago. And the idea is the behavior of nonlinear system can be represented by an infinity dimensional linear operator acting on the observables of the system state. So that means if we have the nonlinear system, and we can use an infinity dimensional linear operator to represent the nonlinear system. So that means by the end of the day, and we have the linear system, and then we can apply the linear multi-agent system theory to solve the problem. However, keep in mind here the states are not for the linear operator, and we cannot use the states of the nonlinear system as a state. So we have to develop some observables, or we have to use some measurement functions as to represent the linear system, or to represent the nonlinear system using the linear operator. So that is something we use the Kaufman operator-based method to solve the attitude synchronization problem of a multi-agent system. So actually here, we use the Quanser's Q arrow, 4Q arrow to do the test. Now I can show you the video. So basically, we want to achieve the attitude synchronization among the 4 Q arrows, and based on the Kaufman method, and the attitude synchronization can be achieved. And this work has been done and published in AWAG GCD in this year. Okay, I think this is pretty much all my slides. So now you can see, I actually at the beginning we talked about the multi-agent system, and we start from the mission file and also the motion synchronization pattern. We apply the pattern technology to solve the synchronized motion between multiple piezo actuators to adjust the gap spacing between the optical instrument. And also, I talked about some cooperative control of multi-agent system, and most on the dynamics and the control part of this topic. All right, so this concludes my talk, and I would be happy to answer your questions if you have.
Thank you, Dr. Shan. The first question is, in your opinion, what are the most important challenges regarding fault-tolerant control systems designed for autonomous systems?
I think we have done some work on the fault-tolerant system, or fault-tolerant control system design for multi-agent system. I think when we designed the fault-tolerant controller for multi-agent system, I think the most important thing is I think we have, I mean, not our group, and I think many researchers have done a lot of work on that. I think, but I think the most important thing is we have to be careful, or we have to understand where are the fault can come from, and for example, we can consider the fault due to the sensor, the fault due to the actuator, and also how much fault will be. I think that is a very challenging problem. So I think, in my opinion, I think we have to realize the reality of the real physical systems.
Thank you. The next question, for the input shaping based consensus method, does each agent need to know the input signal from other agents?
I think each agent needs to know the input signal from itself, because now you can see we have input shaper under, let's say, for example, on this slide, you can see the input shaper has been added to, let's say, if you look at the graph, right, and we added the input shaper between agent 1 and agent 2. So that means the system, or actually the input shaper, input shaping or input shaper, we need to, in order to design the input shaper, we need to get the input from input 1, from agent 1, not from other.
Okay, thank you. For the distributed ILC method, what kind of disturbances are there?
Okay, so that is, let me go back to here. Okay, so I think for the repeatable disturbance, and we consider, as I said, so we consider the cable disturbance as the repeated disturbances, and for the actually for the other disturbances, I believe the system has other disturbances. For example, another example, so is for example, if you have so for example, the system has, let's say we have the gear, and this may be also the disturbance on the system, and something like the imperfection of the system. This could be a disturbance to the system too. But I think for the distributed IOC, we mainly target the repeatable disturbance, which is the cable, the disturbance due to the cable.
Okay. In your distributed control schemes, how would you consider the dynamic changes in the task goals for a group of agents?
So actually, we didn't consider the let's say for the models, and we didn't consider the dynamic change for the models of the agent. However, I think if you remember in one of our controllers, we did consider, let's say, if the communication topology is changing, so that is the switching topology. So we did consider that in our control system design. Maybe this is this answer to you. So we did consider the switching topology in our control system design. So that is one case. And also, how would you consider the changes in the agent itself? The operation conditions of each agent may change the dynamics. Unfortunately, we didn't consider that in our work. So we didn't consider the dynamic change of the operation conditions.
Okay, thank you. The next question, how can we reduce chattering problem in case of sliding mode control?
Yeah, I think this is the very general question, and normally for the sliding mode control, normally for the sliding mode control, so there's a chattering problem. I think we did have this, for example, for the iterative learning control, because we use the sliding mode control. And I think the chattering problem is always a problem with the sliding mode control. I think what we had to do is we have to carefully design the controller and choose the sliding surface, try to avoid the chattering problem. This is my answer.
Thank you. So the next question, what is the delay for the flexible manipulator agents? It means communication delay between two agents.
Yeah, I think communication delay is one reason for the delay, because if you look at if you look at here, we also have the for this full flexible link, and then now you can see the two the two flexible links, they have some delay. I think the question is, what is the delay for the flexible? Actually, let's say when we have the hardware system, and definitely we can for our simulation and even for our hardware test, and we can choose different delays for the system, and also because we consider different communication topology, and we can also add the delay to the system. So I still a little bit confused about what is the delay for the flexible manipulator. Yes, and the delay of the flexible manipulator can have different several reasons, but the communication delay is one of that.
Can the agents in the distributed system be exposed to different external conditions, or do they need to be in the similar type of environments?
Yeah, that's a very good question. And so far, actually for the work we have done and for the work I presented here, so even for the distributed system, and yes, the agent are in the we consider the agent are the same environment or similar environment. We didn't consider very dramatic change of the disturbance or environment to each agent. But I think this is a very good question, and this may be something we are going to do in the future. So far, and we consider all the agents are in the same type of the environment. But I think to answer your question, the first question, can the agent be exposed to the different external conditions? My answer is yes, they can, and also depends on, for example, sometimes when we have the external disturbance or uncertain parameter, and sometimes we set this as long as the disturbance or uncertainty are bounded. So I think that is okay. So that will give us some room for different external conditions. But actually, I have to say, for our research, and we didn't consider they are totally, I mean, the agents are totally in different environment. but I think that is very important because in the future, and yes, and the multiple agents may be in different external conditions. I think that is a very interesting topic to be studied in the future.
Thank you. The next question, could your methods be applied to large-scale system where the number of agents is large?
Well, yeah, I think that is also a very good question, and I would say yes, but also there will be some restrictions, right? For example, the competition load and how big is the communication burden, and I think it depends on if we talk about the communication burden, and then we want to see whether the current onboard computer is possible to address that. I think there are several hardware limitation or restriction. So my answer is that the theory can be applied definitely to the large scale system, but I think there may be some hardware or even software limitation. But so far we have, for example, for the drone, I can say we have 6 drones and we were able to fly 6 drones in our lab. However, if you say whether you can fly 10 drones together, my point is yes, we could. However, it will put a high requirement on the computer, especially for the onboard computer. So I think we did find some issues. If we fly 2 or 3 drones, that is very easy. But if you fly 4, 5, 6 drones, I think yes, and this is really challenging. But I think yeah, the theory can be applied, but I think there's some limitation caused by the hardware.
Could you restate the multi-agent tracking control limitation for non-minimum phase systems?
Yeah, I think we don't consider the non-minimum phase system in our study. Yeah, I don't quite understand the restate the multi-agent tracking control limitation. Yeah, unfortunately, we don't consider non-minimum phase system in our research. And actually, I'm not sure. For example, when we talk about the flexible link, and if we talk about the deflection and also the control of the I mean, because for the flexible link, and we only have the motor, which is control the rotation angle, but there's no control on the deflection of beam. Yeah, so I think this may be a non-minimum system. However, for our research, we don't consider the non-minimum phase system, unfortunately.
Okay, thank you. And probably the last question, what are the current challenges for multi-agent systems, especially multi-agent UAVs, in your opinion?
Well, actually, there are, I have to say, for the challenge for the multi-agent systems, and there have been a lot of work done in this area and the multi-agent system. And yeah, I think there, I mean, research have achieved many achievements in the theory. However, I think the most challenging part, so there are few challenging part for the multi-agent system, especially for the multi-agent UAVs. One is, I think someone mentioned before, so if we want to do the large scale formation or large scale multi-agents by using the UAVs, I think that is very challenging. I think the hardware and those are very challenging. And also, how can we, if we have the large number of the UAVs, and if we want to do the successfully or effective multi-agent or flying of the UAVs, I think how to make sure the UAVs there's no collision, and these are something very important. And also this also plays many changes to the control part and also the navigation part. Yeah, I think there are also many challenges. I would say in the past decade or so, there have been many development in the theory part of the multi-agent system. But how can we apply those theory to the real physical system and to have some multi-agent tasks done. I think that is something very challenging because it poses many challenges to other systems, for example, the hardware and also even the software. And yeah, I think there's many challenges.
So with this, thank you, Dr. Shan, for a great presentation. And I invite you all to check our previous user webinars. As you can see, we have quite a few to share with the audience on different topics. Thanks, and we are looking forward to seeing you at one of our future events. Have a great day, everyone.
Thank you, everyone. Bye.